Yes, sir. Now we can see it.
Can you hear me now?
Yes, yes.
All right. Good evening, everybody. I am Sarath Ramyakumar Kampurapulage. I'm going to present you a lecture regarding tissue processing, embedding, blocking, and microtomy. I think this is a little bit advanced one. I mean, when you compare with your MLT, DMLT syllabus, I have added some more points and updated the knowledge. So I think kindly please attend to this one until the end of the lecture, and please concentrate on the lecture. Right.
Recording in progress.
Right. My first slide is regarding the whole thing, what I'm going to do today. Can you hear me? Hello? Hello?
Yes, sir. I
All
talk.
right. Right. I'm going to do the fixation, tissue processing, sectioning, staining. These are the topics which I have got. I'm going to cover up these things. I think that already Mrs. Subha has done the previous things. So today I'm going to start with the what is called processing first. Right. In the processing, there are three functions that are taken place. Number one, dehydration. Second one, clearing. And third one, wax impregnation. So under the processing, there are three parts, three subheadings to be discussed. There are three functions included in the processing. Number one, dehydration. Second one, clearing. Third one, impregnation. Dehydration means you have to remove the water from the tissue by using a ascending series of alcohol. Now the samples are coming in 10% formal saline. 10% formal saline. Saline means 0.85% sodium chloride. I mean more water. Actually, that means the tissue is totally immersed in a watery medium. But we are going to make it into a wax block. So the water from the tissue should be gradually removed from the tissue. That is called dehydration. So dehydration is taken place by using ascending series of alcohol. So at the final alcohol container, we expect almost all the traces of water from the tissue is removed. Now what has happened? Earlier it was filled with water. Now it is filled with alcohol. Now you have to remove the alcohol. Removal of alcohol is called clearing. So second process is clearing. Under the first one, dehydration. Second was clearing. What is the meaning of clearing? Clearing means removal of dehydrating agent. For that purpose, we are using xylene as the clearing agent. Xylene is the clearing agent. After that, now the tissue already earlier filled with water, then filled with alcohol. Now it is filled with xylene. After that, what we are doing, we are allowing it to impregnation of wax. We are going to impregnate the wax. That means that earlier water, alcohol, xylene, now xylene is replaced by the wax. It is called impregnation of wax. Right? So for that one, we are using water wax baths. Wax baths are maintain the higher temperature of the above the melting point of wax. That means wax should be in the not the solid state. It should be in the liquid form. Then what will happen? All the microcavities, microspacers, and everything will be filled with the molten paraffin wax. So now our processing is completed. Dehydration over, clearing over, impregnation over. Now what has happened? All the tissue is now covered with wax. For that one, nowadays nobody is doing manual thing. All are doing they use the automated tissue processes. There are two types of tissue processes. One is called open, other one is called closed. There are two types of automated tissue processors. One is called open or hydraulic one. Second one is called vacuum one. Now water removed from the tissue and the cells. Now the space is occupied by wax, right? So alcohol are most commonly used in the laboratory for tissue dehydration, since they are miscible with aqueous fixative light, 10% formal saline. In this step, the alcohol penetrates tissue quickly and the water is replaced with the alcohol. So tissue sent through the alcohol series, starting from 70%, 80%, 90%, and absolute alcohol, ascending grade of alcohol. We can use ethyl alcohol, methyl alcohol, isopropyl alcohol, or acetone. But in Sri Lankan setup, almost all the laboratories, they are using ethyl alcohol as the dehydrating agent. This tissue processing involves many steps, on which one of the most important is clearing. Now, that most important step, clearing, which is process of replacing dehydrant with substances which is miscible with embedding medium. Now we are going to remove the alcohol with a solution, some agent, that there is a special property in that agent. What is that property? It should be able to it should miscible with embedding medium as well as alcohol. I mean that intermediate substance that we are taking xylene now. Xylene, that agent should clearly mix with alcohol as well as paraffin wax. That property should be there. So clearing agent should have that two properties. It should miscible with the dehydrating agent as well as the paraffin wax, or the embedding medium. So ideal one is xylene. Xylene is the most commonest clearing agent used in the laboratory, but the problem is it is also hazardous. It is carcinogenic, so be careful when you're using. Alcohol from tissues and cells is removed by the dealcoholization and replaced by the fluid in which wax is soluble, makes tissue transparent. Xylene, toluene, benzene, chloroform, sedaone. So not only xylene, you can use toluene, benzene, chloroform, and sedaone. But there are some plus points as well as disadvantages and advantages. Still, most of the Sri Lankan setup, they are using xylene as the clearing agent. Next one, the empty spaces in tissues and cells after removal of clearing agent are taken by molten paraffin wax. So empty spaces in the tissue and cells after removal of clearing agent are taken by molten paraffin wax in the wax bath. And it hardened the tissue. It hardened the tissue. As a result of it will help to section and cutting. So normally, melting point of wax is ranging from the some wax may be 54, some are having 64, according to your type of wax. Normally, that melting point of the wax is indicated in the label in your wax container. So you have to maintain the temperature of your automated tissue processor few degrees above the melting point of wax. Not 80s or not 90s, just about 5 degrees above the melting point of wax in your wax top. Then this is the automated tissue processor. There are 12 stations. Sorry, I have given the name. Forget about the trade name. I am not biased. I got picture. I cannot cut that one. So 12 stations are there, 1, 2, 3, 4, like that. There are 12 stations, 1, 2, 3, and backside, and finally 12 stations. So this is the remote controller. By that one, you can control, you can program and control. So first one is the formalin bar, formalin jar. First one is the formalin jar. Then after that, 6 jars, grades of alcohol. It's a descending grade of alcohol. Ascending grade of alcohol, gradually ascending grade of alcohol. Then after that, 3 jars for the xylene as the clearing agent. Then finally, like this goes like that now, and finally comes and these are the 2 molten paraffin wax. In these paraffin wax containers, the temperature should be maintained few degrees, about 5 degrees above the melting point of wax, right? So this is the traditional hydraulic type open system. This is called open system, right? And there's another one called closed system. So in this first one, what will happen? We are loading the tissue. There's a bucket here. You can load it here, and whole thing transfer into the next one. Then that bucket comes and immersed inside the solution. Then after certain period of time, program time period, this comes up and go to the next one. It goes like that, and finally completing that cycle, finishing in all 12 containers, right? So this is called open system. But there's another one called closed system. Closed system thing is, in that one, what is called that set of what is called tissues are kept in a constant place, permanent place. Now here in the open system, what will happen? Tissues are transferring from one container to next one. But in the other one, in the closed system, what will happen? The stationary phase is the tissue. Tissues are kept in the same one place. Fluids are move in and move out. Fluids are pumped in and pump out. First one, first solution, pump in. After certain time period, it transfer to the next one, right? Right. So earlier one, close one, the sample, the tissue cassettes are kept in a constant place, stationary place. The fluids are transferring from one to next one. Okay. Right. Now, that's the main difference between the closed system and the open system. Open system, the whole cassettes are transferring from one container to next container. Likewise, it completes the rotation through the 12 containers. But in the closed system, it's different. The samples are kept inside the machine. The first container, first solution pumped into the cassette carrier. After 1 or 2 hours, the fluid transfer out, pump in and pump out. After second one, the second solution pump in, and after 1 hour, second solution pump out. Like that, pump in and pump out system is there. The samples are kept in a what is called that constant stationary pace. So that is the main difference. And the other one, closed system is usually eco-friendly and user-friendly. Why? Always the whole thing is closed now. So you are protected from the aerosol substances, harmful aerosol substances like formaldehyde, xylene, and wax vapor. So you are protected in the closed system. But in the open system, still, because when it goes up and transfer into next one, at that time, the little amount of solution can be come out as a result of your environment, and you are exposed to that toxic vapors. So there are two main differences between closed system and open system. Number one, open system, samples are what's called cassettes are transferring from 1 to 2, 3, like that. Then, but in the closed or the vacuum system, what will happen? The cassettes are kept in a constant place, stationary, and what is called that fluids are pumped in and pump out. That is number one. Second one, open system is little bit, it's not much user-friendly, but the other one, user-friendly. So these are the two main things. So this is the closed vacuum processor or the closed system. Different processing fluids are moved in and out in a single station sequentially. The samples are kept in a single station inside. Here, inside, all the chemicals are arranged here. So one by one, first one, pump in, pump out. After 1 hour, 2 hours, second reagent, pump in, pump out. After next one, third sample, pump in, and after that, pump out. That is the way the vacuum processor or the closed system working. So entire thing is closed. So very little chance to get a risk for you. Why? It is totally sealed. But the problem is this much more costly. Right. The common fault during this tissue processing include brittle and hard tissue due to the prolonged fixation. If the fixation time is prolonged, then what will happen? The samples become brittle or hard. That's the problem. So in that one, how can you correct it? You can correct it by soaking in the solution of detergent. You get the detergent solution and soak it. That is how you making it soft, right? So sometimes the people who are working in the histology department must have experienced that one. Sometimes just like what is called that samples are very brittle, very hard, very difficult to cut, right? So at that time, you can soak it in detergent and you can make it soft. Other tissues like other issue is the insufficient clearing can be addressed by repeating dehydration and clearing processing. Insufficient clearing can be addressed by the repeating dehydration and clearing process, right? So sometimes you get the insufficient clearing. So in that one, you can add the several saline baths. Clearing is not sufficient. So instead of 2 baths, you can add 3 clearing baths, 3 saline baths. The various factors influence the tissue processing, such as size of the tissue. That's the reason we are telling the sample should be very, very thin, and the temperature and the viscosity and the negative pressure. All these things are having an impact on the processing. What are the factors influencing for the tissue processor? Number one, size of the tissue. Second one, temperature. Third one, viscosity, and then negative pressure. The tissues are processed mainly by automated tissue processors, which are two types. One is tissue transfer process and the fluid transfer. Then now I have already explained you. One is tissue transfer processor, that is the open system. And the second one, fluid transfer processor, that is the closed system. Then these are the things you can expect. Shrinkage of tissue. These are the errors you can expect. What are the errors you can expect in the processing? Number one, shrinkage of tissue. Shrinkage. So optimize fixation. Use a phosphate buffer formalin solution. Instead of 10% formal saline, you can use the buffered formal saline. Then dehydration. Follow gradual ethanol series 70, 90, and 100 with each 15 to 45 minutes. So these two methods can be used to overcome this problem. But the shrinkage of tissue. Tissues are shrink. Second one, retain air samples. Air in the sample. In the sample inside, air is retained. So this can be done. This can be you can solution for that one. Submerge the tissue fully in a fixative like formalin immediately after collection. After collection of tissue, don't leave it in the environment. Immediately after grossing, samples should be totally immersed inside the formal saline. It will prevent the formation of air in the sample. And the trim and maintain. And you can trim the sample and you can remove the what's called trim samples. And then the sample size is small, the chances is low to carry the air. Next one, poor embedding or infiltration. Poor embedding. When you are wax embedding, focus on clearing. Orient and use quality wax. You have to focus on clearing and orientation and use the quality wax. And you must use the trained staff to handle the tissue gently. So by doing those things, you can remove that. You can avoid this problem, poor embedding or infiltration. Then preventing mistakes in tissue processing is crucial, especially in diagnostic when compromised samples can lead to no diagnosis and patient distress. So that means if you are not doing the processing properly, it will make big problems. So that means that's the reason what I am telling the processing is crucial. Processing is crucial. It should be done in the correct manner. Errors often arise from poor scheduling. Now the process, we have to schedule the time now. Sometimes if your schedule is wrong, errors can take place. In inadequate fixation, the fixation time is not sufficient, or neglected reagent. Sometimes the reagent negligence. That means reagent means reagents are old reagents, right? You have to change the reagents oftenly, or otherwise what will happen? The old reagents give a lot of problems. And the other one, you have to maintain the levels of the reagents. In the automated tissue processor, always you have to, in the morning, you have to check whether the levels are enough. If the levels are not enough, you have to fill it. Then to avoid these match processing schedules to issue type and size, avoid short runs for large. If the tissues are large, avoid short runs. If the tissues are large, the better to go for the, long runs. That means that don't do it in 6 hours or 8 hours. The whole cycle should go for about at least 20 to 22 like that, 22 hours so like that. Some people cut short the run, what is called program. Some people program it for 6 hours, 8 hours. So those things are wrong, because if you are making short runs, what will happen? The large sample, that large tissue will not be correctly processed. Fix specimen in formalin immediately after collection adding extra time in processor if needed. Some people add formalin, first one in the formalin, first container filled with the formalin. Replace ethanol, xylene, and wax per strict guidelines using tools for quality control. And you have to do the quality control. This is one of the quality control method. What is that? Replace the ethanol, xylene, and wax according to your guidelines, right? Don't leave it for a longer time. Don't leave it for 2 weeks, 3 weeks. So when the time with the guidelines say 1 week after change the one week's time, so you have to adhere to that one. Handle tissue gently during embedding to avoid fractures. Using heated forceps, just warm enough to melt it. Some people, they break the tissue by using heated forceps and other things during the embedding. There are maybe fractures in the tissue. So avoid fractures. It will damage the tissue. So always do handling should be done in gentle manner. And again, I'm telling, train staff thoroughly on techniques from dissection to embedding to reduce the human errors. So if you want to reduce the human errors, you have to apply, you have to train people should be employed there. Then how do you, now I told you, now that's very critical issue, dispersal of used xylene and chemicals. Xylene and chemicals both are harmful chemicals. Formalin is a carcinogenic. Xylene is also carcinogenic. So you can't just dump into your what is called day-to-day wastewater, right? So you have to pay attention for that one. You have to apply 3R system. What is 3R system? Reduce, replace, and recycle. Reduce the use, reduce the xylene use, reduce the alcohol use, reduce the formalin use, and replace it. You can use some other substitute. Instead of xylene, you can use some toluene, benzene, like that. And recycle. You can use the recycle machines. Now, recycle machines are commercially available. You can purchase it, and you can, by using recycle, you can obtain 99.9% xylene from the used one. So that these are the things you have to apply 3R system, reduce, the replace, and the recycle. Bio-friendly substitutes can be used to reduce the use of xylene. Xylene is not bio-friendly, so you can use some bio-friendly substitute like sedout oil and other things. You can use those things are bio-friendly, user-friendly. Then how do you dispose? Incinerate. Xylene can be incinerated at high temperature, which destroy the hazardous compounds. But you can't do it in your laboratory premises or the outside because you don't have facilities. Then you have to use a incinerator that very high with a high chimney. What is called that means that after burning, that it should not come to the what's called our level. What's called, it should not come to the ground level. So that means very high with a very high chimney you can use in the incinerator, right? So otherwise you can hand it over to the places like Sicilianaro. There are some places commercially, they are commercial agents are there. They are buying those things. They are taking those things. You have to pay something. Then they are doing the incineration, right? Or landfilling. But in Sri Lanka, you can't do it. In some other countries, you can landfill in the deserts. Far away deserts, you can take and landfill in the deserts. Xylene can be landfilled in a secure landfill that is designed to prevent the waste from the leaching into the environment. So there is no chance to leaching into the environment because you are going to landfill in the desert. Right now, there are 3 methods to what's called dispose xylene. No, control xylene. Number 1, reduce, replace, and recycle. Then one method. Second one, incinerate the saline in the high temperature. Third one, land filling. So these are the ideal ones. But in Sri Lankan setup, I have seen this is not practiced in Sri Lanka. That's very sad thing, right? They are just putting into the wastewater this thing. It is totally wrong. It will be a problem for the environment and for the what is called that water line, tap line, and all these things will be damaged. Don't do it. Then recycling. For xylene and the contaminants are mostly alcohol. In the xylene, the contaminants are mostly alcohol, biological materials, and paraffin. The contaminated alcohol is distilled into the waste container, and the pure xylene is distilled into the separate container. So when you are doing recycling, xylene is coming to one container, and the other things are coming to the other container. Paraffin and biological material remain behind the boiler and removed through the drain. From the drain, biological material and the paraffins are coming. So you can take the alcohol and the xylene in that machine. Recycling xylene substitute follows the same procedure, except the xylene substitutes have a higher boiling point than the xylene. I told you, you can use the xylene substitute. Instead of xylene, you can use some other chemicals. Their boiling points are very high. Then you have to, if you are using a recycler, you have to go for a very high temperature. That's the problem. So this how you are going to dispose the xylene. Sorry, formalin. Formalin is discarded. I have seen most of the Sri Lankan laboratories, what they are doing is they just dump into the wastewater. It is totally wrong. When I asked from the Viva in the university students, they also tell dilute and put into the what is called septic tank. Totally wrong. If you allow it to go into the septic tank, what will happen? Septic tank will be destroyed because these bacteria that formalin go and kill the organisms. That our septic tank, that function will be affected. So do not allow the formalin to go into the septic tank. It is a wrong procedure. So before you release to the drainage, what you have to do is you have to neutralize the formalin. Without neutralizing the formalin, don't release to the drainage. It is a wrong. It is a crime, right? Without neutralizing the formalin, don't release to the drainage. It is wrong. So you can neutralize the formalin. That's one method. And the second one is you can recycle by using a recycle machine. In the neutralization, how do you do it? You can do the acid or alkali neutralization. You can do the acid neutralization or alkali neutralization. In the acid neutralization, you can use acids like acetic acid. In the laboratory, easily. Vinegar, acetic acid, you can use cheap one. You can add small amount of amounts, I can't remember the amounts, small amount of acetic acid and add to the formalin, leave it for about 24 hours. And tomorrow what will happen? Tomorrow everything will be neutralized. Then after that you can release to the drainage. Second one, alkali neutralization. You can mix with the sodium hydroxide. Sodium hydroxide is a very cheap chemical, right? Don't go for the very high grade, what is called that very high grade expensive chemical. Just what is called not the analytical grade, right? Just what is called just sodium hydroxide, right? Not for the analytical grade though. It's not be purified. Just sodium hydroxide and 2 molecules of formaldehyde react with sodium hydroxide, one sodium hydroxide molecule, and it will form according to the Canitz-Arrow reaction. Have you heard Canitz-Arrow reaction? That formaldehyde and sodium hydroxide giving methanol and sodium formate. So methanol and sodium formate you can release to the drainage. So there are two methods: neutralization, acid neutralization, alkali neutralization. So my question: how do you dispose the toxic chemicals? Toxic use chemicals in histopathology. So if you get that type of question, formalin, you have to mention about formalin and silane. Silane, how you do? 3R system, or what is called that incineration or recycling. Formalin, how do you do it? Again, you go for the 3R system. At the same time, you can do the alkali or acid neutralization. For the acid neutralization, add acetic acid. For the alkali neutralization, you add the sodium hydroxide. And after one day, you can release to the drainage. And the other one, you can do the recycling also. Recycling formally, you should choose a solvent recycler that uses the fractional distillation by temperature. In different temperatures, different solutions are come up. If the concentration is too low, the tissue will decay, and if the concentration is too high, the tissue will become tough and difficult to cut. So that means your formalin should be ideal. If the formalin is very much diluted, concentration is low, what will happen? The fixation will not be taken place. If the concentration is high, the tissue become tough and difficult to cut. So you must know which level of formalin should be there. Then high quality tissue processing demands sound procedures, quality materials, and meticulous care. So when you are expecting high quality tissue processing, so you must have correct procedures, exactly correct procedures. You have to follow the correct procedures, and you have to use the quality material and the meticulous care. You have to do it with a very much care. Then tailor schedules to tissue size and type. So according to the size and type of tissue, you have to schedule can be changed. Like 6-hour run for 4 millimeter samples, adjusting for a large or denser tissue. Like that, you can adjust the run, 6-hour run, 8-hour run, 10-hour run, like that. The time period can be adjusted according to the type of tissue you are using. And invest in modern processor with vacuum or the pressure cycles and fluid circulation on uniform, fast results. That is the ideal one. I'm recommending that one, but the problem is very, very costly. So you have to think about the budget also, right? So investing modern processor with vacuum or the pressure cycle and fluid circulation. So that is very fast results. Problem is money, budget, very high, very costly. Then refresh ethanol, clearing agents, and wax regularly. Don't leave it about 2 weeks, 3 weeks. Regularly, you have to change the thing. Check embedding center, hot plates, and wax reservoir to prevent the heat damage. Temperature of the embedding center, wax temperature should be checked. Wax reservoir, you have to check the temperature. Otherwise, if the temperature is very high, tissues become barbecued. And finally, it will become brittle. So always you have to control the temperature of the embedding center. Orient tissue precisely in molds for the correct plane of tissue. You have to orient the tissue in the correct direction, correct way. Orient the tissue precisely in molds for the correct plane of tissue. Then you get the correct plane of section. Select premium paraffin with additives for hardness and elasticity, enabling thin ribbon-like section. So ideal, good quality paraffin wax. Don't use the commercial purpose paraffin. Do not use. Those things are very cheap, but never use those things. You have to get the analytical type one. Otherwise, you can't get the thin ribbon-like section. You can't get. Then document process. Everything should be documented. All the steps should be documented. That's a compulsory. Reagent changes, equipment back checks, troubleshoot. Those things are very important for the troubleshooting. I mean, each and every step should be documented in the laboratory. It's very, very important. Those things are very important for the day-to-day functioning, correct running. These practices deliver consistent, high-quality paraffin-embedded specimen for sectioning, staining, and analysis. So if somebody asks, what are the steps to be followed to have a very quality laboratory functions in the histopathology? So you have to mention these points. Embedding with molten wax. Embedding in histology involves orient tissue in mold, pouring paraffin, solidifying it in a cold plate. Everybody knows that one, no? Embedding, how we are doing, take the mold, add the paraffin wax, and after that, by using a forceps, add the tissue into that one in the correct plane, correct position, and after that, allow it to solidify in a cold plate. Step of embedding in tissue processing: dehydrate and clear tissue, melt paraffin, embed tissue vertically, solidify paraffin, remove from the block. So these are the things in the process, in the embedding steps: dehydrate and clear tissue, then melt the paraffin, embed the tissue vertically, solidify the paraffin, and remove the block. Embedding is histology's crucial step to prepare tissue samples for sectioning and microscopic examination. So embedding is a crucial step. So there are different molds: paper molds, metal mold, demock mold, disposable mold, metal or plastic mold used for ring cassettes, right? So normally in our laboratories, we are using metal molds. So this is the automated embedding center. So these are the molds. You can see molds are, metal molds are there. And this is the automated tissue processor. There are magnifying glass, light, and all the things are additional things. Those are helping to do the correct embedding. Wax reservoir, wax is kept inside this one. Then heated area for steel molds. The steel molds are kept in the heated area. Then wax dispenser. You can see wax can be dispensed here. That's wax dispenser. Once you press the thing, wax is dispensed to the mold. Then separate hot and cold plates. These are cold plates, and the hot plates also there. Then when after embedding, you keep the what is called mold filled with the wax should be kept inside. So after that, you can remove it. So this is the automated embedding center. So these are the all type L-shaped pieces we used during the manual processing. Now we don't use it. Now directly taken into these molds and covering with the cover of the cassette. Right? These are the cassette cover. This is the cassette. The tissue is kept inside. Open the cassette, and you can we can keep it on the top of the mold. Right? Mold filled with the wax. Place the tissue in the center, and after that, keep this one on the top of that, and keep whole thing at the cold plate. So in about 5 minutes time, it will solidify it, and after that you can remove it. The block can be taken out. So these are different cassettes. Some are tissue cassettes, some are biopsy cassettes. In the biopsy cassettes, the pore size is small. So when you are purchased also, you can, so the MSD, biopsy cassettes and tissue cassettes. Some people are thinking both are same. No, not both are same. For the biopsies, the pore size small. The tissue cassettes, pore size large. And different colors are taken. That's ideal because urgent one or neuro samples, renal samples, and all these things can be taken into different cassettes. So go for the different cassettes and use the biopsy cassettes and tissue cassettes. Biopsy cassettes are having small pores. Tissue cassettes are having large pores. So these are the different type of embedding media gelatin, celluloidine, artificial resin, polyester wax, polyethanol glycol, PEG, and polypene, that's a commercially prepared one, and epoxy resins, and the polyester resin, and the methacrylates, especially for the EM, electron microscope users. But in Sri Lankan setup, we are taking but it's called paraffin wax as the embedding medium. Paraffin wax we are taking. Tissue orientation is very, very important. The specimen is very carefully oriented in the mold because its placement will determine the plane of section. The plane of section is depending on the orientation, how you are going to keep the tissue inside the mold. That's an important consideration in both diagnostic and research histology. Paraffin wax quality and composition, paraffin wax with a higher melting point used for embedding, mold size, cassette type. So there are 3 types of molds, 3 sizes, and the cassettes also different cassettes are there. Mold also different sizes are there. So if you are taking a small biopsies, take the smallest mold. Actually, the molds are same size, but thing is, in the well, just like a well-like thing, no, that is small in the smallest one. Take that will be suitable for the biopsies. And if the well, that bottom, if the bottom is large, it can be used for the larger sections. The bottom is smaller one can be used for the biopsies. And availability of light, that also important when you are doing the embedding. That's the reason the machine is having a light. So all these things are supplied, provided in the automated tissue processor center, embedding center. Automated embedding center, all these things are provided. The correct orientation of tissue is very important for the proper cutting and microscopic examination. So correct orientation. So when you are doing the embedding person, he must be having a thorough knowledge about the orientation of tissue. Otherwise, when you are cutting, the cutting person have a lot of problems and you can't get the target. Tissue is usually placed at the flat on the central part of the mold. How you are going to keep this tissue? Okay, tissues are usually placed at the flat on the central part of the mold. At the center, you have to keep it flat. It should be oriented in such a way so that cutting is easy by knife or microtome. So it should be able to easily cut. If it is slanted, angle, what will happen? So when they are cutting the microtome, the whole section will not come into the section. So that means plane of the section and the plane of the plane of the block should be parallel. Plane of the section and the plane of the block should be parallel. Then when you are doing the microtomy, whole section comes into the section. Whole tissue will be come into the section. Orientation. Proper tissue orientation is essential. How the tissue is placed in the paraffin block determine the plane of section and the structure that will visible under the microscope. So that means that orientation very, very important, very, very crucial. Depending on the orientation, it determines the plane of the section and the structure that will visible under the microscope. The paraffin quality. It is essential to use high quality paraffin wax with the correct melting point. Recently, one of the MLT told me that they got the commercial type paraffin wax, and each and every time the paraffin wax that from the mold, from the block, always detached from the cassette. So very difficult to manage. So don't use low quality paraffin wax. Go for the analytical type one. Analog grade. Tissue requires special orientation, especially tubular structures, arteries, veins, fallopian tubes, and vas deferens. So you must be able to cut in cross section of the lumen. So if you have a tubular structures like arteries, veins, fallopian tubes, and vas deferences, you have to be able to get the cross section of the lumen. Okay. the final section should be round in shape. Even the tissue is linear-like thing, just like worm-like thing, right? But the section should be a cross-section of the lumen. That's the way you have to embed it. So see how you are going to tubular tissues should be embedded like that. That all the labels, all the levels of the what is called tube, you can take it. But if you are keep it in the this shape like that, if you are keep it in the longitudinal way, it is wrong. So this is actually transverse cross section like that. Tubular tissues are embedded like that. This is how you are going to embed the skin. All the layers should be, you should be able to get all the layers. Dermis, upper dermis, here. Dermis, upper dermis, dermis, fat layer, and all these things should be able to taken into one section. So endometrial curetting, small biopsies and other things, all the things are kept in the center, at the center, very much close to each other. And everything should be same depth, same depth. That means the one section, all the sections are coming. All the tissues are coming into the one section, right? So after keeping, make a press, just press the tissue by using a heated forceps and bring the tissue to the bottom of the section. If the sections are kept, if the sections are blocked in different layers, what will happen? The whole section, all the tissues are not coming into the one section. So longer tissue, you keep the long tissues, you just keep it like that, longitudinally, like that. Intestine, you should be able to get all layers should come. All layers should be able to get. And the other one, like that tubular-like thing that you can, just like a Swiss roll, right? Right. Next one, wax embedding. Here what you're doing, take the mold, take the metal mold. See, the bottom is very large. Then this can be used for the larger sections. So filled with the paraffin wax from the dispenser. And after that, take the tissue and place at the bottom. See, all the things should be added into the mold. And after that, using that cassette, you can cover it. And whole thing should be kept in the cold plate. The cold plate. Right. See how you are taking. Right. So this is the wax embedding with the wooden. Those days we did it like that. By using L-shaped pieces, and after that, those days we didn't have this type of cassettes. We didn't have cassettes to cover. What we did it, we used a wooden piece. Then after that, you take it out. The wax block is attached to the wooden piece. The whole wooden base and the whole thing can be fixed onto the microtome. Now, I think in Sri Lankan setup, I mean, nobody's using those things, but about 25, 30 years back, most of the laboratories, they did it like that. Nowadays, no one is using this wooden block. Advantage and disadvantage of the automated tissue embedding system. What are the advantages? The automatic tissue processor is especially valuable in high volume laboratories where time and consistency are critical. So you can use for number of samples. You can control but you can time management and the number of samples. It reduces the need for manual labor, minimize human error, and improves the lab. So these are the advantages. What are the advantages? Need for manual labor, minimize human error, and improve the lab. What are the disadvantages? Inadequate vacuum cycles in automated tissue processors, especially fluid transfer models fail to remove air, compromising quality. These are the reasons, and these are the disadvantages. And inadequate vacuum cycles in the automated tissue processor, and especially fluid transfer models, and fail to remove air, compromising quality. Dense or porous tissues are especially prone as air pockets persist, hindering uniform processing and downstream analysis. The dense, thick or porous tissues which are having pores, especially they may carry air pockets and giving problems. That wax embedding will be affected. Then microtome, section cutting, rotary, sliding, freezing, rocking, based sledge. Nowadays, there are some other names also, mainly these type of 5 types, but nowadays there are some more microtome types are there. In a Sri Lankan setup, they are using rotary type, that is rotating. This is a wheel, this is a wheel, this is a handle. This by using this knob, you can control the thickness of the section. This is the block holder. There's a block here. Angle can be changed by these knobs. And the knife is kept here. Nowadays, nobody is using knives. Instead of that, disposable blades are there. There's a blade carrier, and the blade can be kept inside. This can be pushed upward, backward, and forward by losing this lever. There's this thing, you can lose it, and you can push it there, or you can pull it, right? This is the traditional rotary microtome. Advantage of rotary microtome, ability to cut 2 to 3 millimeter micrometer sections, heavier, so more stable, large and heavier knife use, less vibration when cutting hard tissues. Cutting angle of knife is adjustable, easy adaptation for all types, hard, fragile, or fatty. So you can cut hard tissues, bony tissues, fragile, breakable, and fatty tissue. For all tissue types, this is suitable. Can cut celloidine embedded section by using a special holder to set the knife obliquely. So you can not only the paraffin wax, celloidine embedded section also can be used by using a special holder. Ideal for cutting serial sections, large number of sections from each block. So fully automated rotary microtomes, some laboratories you have 2 motors that drive both the fine and the coarse advanced hand wheels. You can use the fine advancement, and the coarse advancement can be done with the 2 motors, right? This is the fully automated, but I never recommend. That is up to you, your choice. Very expensive. You can purchase about 4 or 5 microtomes, 4 or 5 manual microtomes of the cost of the fully automated microtome. If the MLT is qualified, and if the MLT is having good quality, if you know the technique, ideally what is called manual one will be ideal. So these are the equipments for the paraffin. What are the equipments required for the paraffin wax section? Water bath, drying oven, fine pointed or curved forceps, small squirrel hairbrush, clean slide, ice tray, pencil, and teasing needles. Section adhesives. So most of the people use albumin, but I do not recommend it, because most commonly used adhesive is albumin. Others are starch paste and chrome gelatin. Albumin solution prepared by mixing equal parts of glycerine and distilled water and white of egg white albumin. Then filtered through coarse filter and crystal of and add the crystal of thymol. You are adding the thymol as a preservative. What are the disadvantages? Albumin retains some of the stains and gives a dirty background. It retains some stains, different colors, and gives dirty background. And thymol resistant organisms growing and adhesive have been known to cause confusion in gram stain section. For the gram stain, when you're doing the gram stain, the thymol resistant organisms will grow on that one and giving problems. Sometimes bacteria grow on the albumin and you may think this bacteria originally found the tissue. Ideally, there are two adhesives are favored, poly-L-lysine and 3-aminopropyl triethyl xylane or the EPS or charge or plus slide. I recommend these things especially for the immunohistochemistry. For the immunohistochemistry, if the section is detached from the section, our entire process is lost. We are having a big, what is called loss and disadvantage. So that means you have to make sure the section will not detach until the end of the procedure. So that's why I recommend poly-L application of apply the poly-L-lysine on the slide. That is number one. Or use the EPIS or the charge or plus slide. In this slide, permanently positive charge. The slides are having a coated, so the slide is having a positive charge. Sections are negative charge. The tissue sections are negative charge. So according to the positive negative interaction, the tissue is tightly attached into the charge or the plus slide. So there are two slides, poly-L-lysine application. Stick the slide section onto the slide. Second one, 3-aminopropyl triethoxysilane, EPS, charge or plus slide. There's a charge on the slide. According to the plus and minus interaction, the tissue section is minus charge. This side is positive charge. So positive negative interaction, the section is tightly bound to the section until the end. Technique of cutting. So I think you all are familiar with that one. I just rush into that one. Insert the knife in the knife holder and screw tightly. Fix the block in the block holder. The block should be in the block holder, knife in the knife holder. Feed mechanism is adjusted until the wax block is almost touching the knife. The mechanism is adjusted until the wax block is very much close to the knife. Ensure that whole surface of block will move parallel to the knife so the straight ribbon of section is obtained. That means the angle of the section should be controlled. All screws should be tight to avoid faulty sectioning. First, you do the blocking. How you are doing blocking? For blocking, trimming section, thickness 15 micron, around 15 micron, with rough knife is taken. After that, keep the slide on the ice tray, and after that, take the sharp knife and do the sectioning for the thickness of 3 to 4 microns. Nowadays, nobody's used these knives. Most of the laboratories, they use the disposable blades are used in the most of the laboratories. Now it is easy, not necessary to go for the sharpening of the knife. Reset the thickness gauge to require the thickness, right? Apply ice to the block surface to make the wax hard, which should have become soft. Sometimes with the temperature, the temperature that this become what's called warm. So if the section is warm, you can't cut. So that's the reason we keep it and keep the allowing touching the surface of the section with ice and allowing to cool it. When it cool, it is easy to cut the section. There should be a smooth, continuous plastic flow of the section in the to form a ribbon. A ribbon should come out. When the ribbon comes off, it is held gently with a fine moistened brush or forceps and then transferred to the water bath. In the water bath, what will happen? If you have creases, folding and all these things, you can remove by applying brush. Section in then floated on the water bath. Temperature 5 to 6 degrees below the melting point of wax. If the melting point of wax is 55, the water bath temperature is 50. Like that, at least 5 degrees lower than the temperature of the melting point of wax to remove the creases, foldings. Clean or albuminous slide is half submerged in water and section is picked up using a dissecting needle. Slide is then set in upright position, drained. Slides are kept in incubator overnight and plain slides and 60 for the 2 hours for the albuminous slide. But I am giving one advice. If you are going to do the immunohistochemical, never use 60 because at that temperature, all your antigens will be destroyed. So I have seen in some laboratories, after cutting, sections are kept in oven, the temperature will be above 60. It is totally wrong. As a result of that, your entire immunohistochemistry will be failed. Why? At that temperature, most of the antigens are denatured. So if you are going to do the immunohistochemistry, so definitely site should be 37 degrees. Overnight will be ideal. So this is the microtomy, how you are doing the microtomy. You can see, rotate in the wheel. The sections are coming in a ribbon-like manner. You can select the ideal section. You can use the forceps and select the ideal section and putting into the warm water bath. Temperature should be 5 degrees lower than the melting point of wax. Slide should be submerged, half merged, and removing the foldings or the creases. Then after that, slide taken out and store in the 37 degrees. The microtomy sectioning, the microtomy can be set freely, but keep in mind that there are number of factors that determine the actual section thickness. The thickness of the section can be conditioned by various factors, such as the rotation speed. When you are rotating, rotation speed should be constant at the angle of incline of the blade and the state of the blade. The blade should be a new one. If the old blade, the section will not be ideal. The temperature of the block is one of the most important factors affecting the thickness and quality of the section. Earlier also I mentioned, temperature of the block is very, very important. Don't keep it in the block holder for a long time. What will happen? The temperature will be increased. So after that, if you want to take more section, remove it from the block holder and keep it on ice again, and again you can cut it. Even the type of block affect the thickness, especially during the trimming. Even the type of tissue, soft or hard, affect the thickness, especially during the trimming. Microtomy troubleshooting, this is also very important. How do you do the troubleshooting in microtomy? This is the answer for that one. Use a different part of the blade than one used for the grossing. So in the blade, you are trimming one area now. So shift it some other place for the cutting. And if the front of the block becomes warm, it may be necessary to further cool. Understood? Generally, the best results with minimum compression and obtained with the slow and uniform cut. Do the slow and uniform cut. Do not interrupt and restart the cutting process because bands of different thickness will form along the section. That your rotation of wheel should be in the uniform manner. Do not interrupt in between and do not restart during the cutting process. You have to continue into a uniform speed. Before cutting each section, in some laboratory, it's common to lightly blow on the front of the cold block. That is ideal. I have seen some experienced MLTs. They blow by your mouth to the section while you are cutting. You blow because in that one, it make it cool. You can make the block cool by blowing a new air from your mouth to the cutting section. If a block is difficult to cut because it's hard or crumble, the surface can be immersed in the bath of cold water or emollient agents such as softener. Earlier also I mentioned a softener can be used, a mild detergent. Then you take the section, if the section is hard, you remove the block and submerge inside keep it inside the cold water or mild detergent. Then what will happen? The hardness will be disappeared. For calcium-based sample, it is possible to obtain section by applying a descaling agent for the exposed tissue for 10 minutes or more. You take the formal nitric acid. This is the decal agent. You take the section. You can, if you feel the hard calcium parts are there in the tissue, you take out the block from the machine and immerse in mild decal agent like formal nitric acid. Formal nitric acid is a mild decal agent for about few minutes. Then what will happen? It will do the surface decalcification will occur. Surface will be decalcified, right? Some people use very dilute nitric acid also, very diluted nitric acid also. In that one, surface decalcification will be taken place. Then after that, you can cut the thing. So this is tissue microtomy, trimming of tissues, then cooling the wax block, then cutting the tissue, making the ribbons of the section, put into the warm water bath, then sections are coming out. Sections are taken with the slide. This is the end of the presentation. Questions are what is called, if you have any question, it is the time to ask. If you have any question, please raise now. Participants, did you follow? Did you understand my lecture? Please reply. I want a feedback. Anybody can reply? Did anybody? Hello. Did you understand the thing? Did you follow? Did you able to understand? Can anybody reply to me? Just say yes or no. Hello, can you hear me? Participants, can you hear me? Participants, can you hear me? Can anybody tell me if you have any difficulty or if you have any problem, please raise now. Hello. Hello. If you have question, please raise your question, please. Hello. If you have a question, please raise me now. Mr. Murugadas, if you have a question, please ask now. Can you hear me? Hello. Can you hear me? No answer. Hello. Can you hear me? Yes. Okay. Right. Then I'm going to start my second presentation after exactly 5 minutes. I'm giving a 5 minutes break. After 5 minutes, immunohistochemistry A to Z. Immunohistochemistry A to Z, I'm going to explain in a short period of time. I expect all of you are presenting for that lecture. I'll start in another 5 minutes time, right? Okay.
Hmm. Hmm. Hello. Hello, Patieni. Are you here? Yes, I unmute. Patieni, I will give you to host. Can you hand raise so I cannot identify you? Hello. Lakayani, kasi hatak kidhar hai? Hello. Now you all can switch on your mic, but better to mute it.
Hello, Dinesh.
Yes, I will give you host because I have some work today.
Oh, okay, okay.
Over I also I gave him
Gimana? Dinis gimana? Ay, di marami naman nakaraan. May gawa. May lain apat silong. Apat silong.
Hello, sorry, there was a delay regarding the technical problem. So I'm going to start the principal methods, clinical application of immunohistochemistry. With the time, I'm going to rush. I have to rush it. Right. Definition of immunochemistry. All of you are knowing the definition. Immunohistochemistry, immunohistochemistry. 3 words, immunohistochemistry. Immunohistochemistry is technique for identify tissue constituents by means of antigen antibody. We are going to identify the antigens in the tissue by means of antigen antibody reaction. Simple. Immunohistochemistry is a technique for identify the tissue antigens by antigen antibody reaction, right? So antigen antibody reaction is happen. Then how do you going to identify the how do you know that antigen antibody reaction happen? So you need some sort of label. With the label, you can identify the completion of antigen antibody reaction. The site of antibody binding being identified either by direct labeling of the antibody or by the use of secondary antibody labeling the method. You can use the direct labeling or the secondary antibody labeling. So immunohistochemistry is a technique. You are going to identify the antigen by antigen antibody reaction. How do you going to identify the antibody-antigen reaction? By the direct labeling of the antibody or the use of secondary antibody labeling. Then antigen and antibody, I'm not going to discuss much about this thing. You just go through what is antigen and what is antibody. For my lecture flow, I am giving these things, but actually this is an immunology subject. But I added because sometimes some people may not be knowing about antigen and antibody, what is antigen, what is antibody, and the other things. So that's what I reminded. So I'm not going to go into details. So this is the general antibody structure. So antigen antibody, what is called that binding, that also there. I'm not going to discuss those things, but there are 4 words: affinity, avidity, specificity, and sensitivity. These 4 words, when you talk about the immunohistochemistry, these 4 words we are using. What is affinity? What is avidity? What is specificity? And the other one, sensitivity. There are 4 words. The meaning is given here. Right. So there are 2 things called, one is called polyclonal antibody, other one is called monoclonal antibody. In the polyclonal antibody, you can see the antigen, there are antigen epitopes. There are different tomographical areas in the antibody. These are called epitopes, antigen epitopes. So these antibody. This is a polyclonal antibody. This antibody is specific for these epitopes, red colored one, these epitopes, and this one. So this is called polyclonal antibody. That means it is specific for different epitopes. But in this one, monoclonal antibody, it will specific only to one type of epitope. So this is monoclonal antibody, this is polyclonal antibody. Then preparation of specimens, there are myths. Most of the time they thought when the formalin fixed paraffin embedded tissues, they destroy the antigen, but it is not destroy. What will happen? The many epitopes are masked by the formalin. These are masked. So many antigens are not lost, but are masked by the process involved in the fixation and paraffin processing. Then choice of immunohistochemistry specimens to suit the need of particular type of work governed by some. There are 4 types of samples can be used. Frozen section can be used. Cytological preparations like cytospin samples can be used. Formal fixed routinely processed paraffin sections, and the resins and plastic embedded. So what are the types of specimen can be used for the immunohistochemistry? Frozen sections, cytological preparations, formalin fixed, routinely processed paraffin sections, resin and plastic embedded material. All 4 can be used. Recently, one of the senior MLT argued with me. They asked me how you are going to do the frozen section, immunohistochemistry in frozen section or the cytological preparation. No, you can do. Cytological preparation, my recommendation is cytospin. When we are doing the cytospin, you get the uniform smear. So all 4 can be used for the immunohistochemistry. So it's an important histological tool. All the use is decreasing. Certain inherent disadvantages compared to the paraffin sections include poor morphology. When you are doing the what is called that cryostat or the cryostat sections or the frozen sections, the morphology is very poor and the limited retrospective studies and the storage problems. So we very rarely only we are doing the paraffin wax sections. Mute to mic. Right. Then cytological preparation. Those cytological smears are fixed in acetone. Acetone fixed smears or cytospin are preferred. Acetone allows a wide range of primary antibody. Many antibodies still insist on alcohol fixation. Smears, imprints, cytospin should be air dried for 1 to 3 hours and then fixed or stored as out of line for the frozen section. Haley solution, B5 fixative, those can be used as the fixed settings. So cytological samples also can be used. Third one, formalin fixed routinely processed paraffin wax technique. To achieve the reproducible and consistent demonstration of antigen with the minimum background staining while preserving the integrity of tissue architecture. So you have to have the background should be minimum. Background staining should be minimum. If the background staining is more, so not ideal. Adequate and appropriate fixation is important, gives morphology and antigenicity. So if the appropriate fixation should not be over fixation or under fixation. Under fixation and over fixation is wrong. It should be ideal fixed. It should be adequately fixed. So demonstration depend on the fixatives and the IHC method. So our demonstration depending on 2 points. What are the points? It depends on the fixative and they depend on the method which you are using. Most commonly, right, this is very important. Most commonly used adhesives albumin. Others are starch, paste, and chrome gelatin. But the thing is, I'm not recommending all these things for the immunohistochemistry. Only poly-L-lysine or 3-amino propyl triethoxysilane, APS, or charge slide or plus slide. These two slides are used for the immunohistochemistry. Don't take any other type of slide. Never use use either poly-L-lysine slide or the charge slide for the immunohistochemistry, because you must make sure the sections are not detached until the end of the procedure. If the section is detached during the procedure, it is a big disadvantage, right? It is a loss. So take what are the adhesives, what are the slides you are using? Poly-L-lysine slides or charge slide or plus slide. Then this is the technique. If somebody asks what is the technique, mention the technique of immunochemistry. This is the one. First, you cut 3 to 4 micron sections and place on the clean glass slide. Dry section overnight on 37. Never kept in the oven. If you kept in the oven, what will happen? The high temperature destroy the epitopes, antigens. So dry section in overnight in 37 degrees. This is very, very vital. And dewax in saline and bring to alcohol. This section is covered with wax now. So remove the wax and bring to alcohol. Then rehydrate using descending grade of alcohol. Understood? So you have to bring the section to water level. Why? The stains are dissolved in water. So dehydrate using descending grade of alcohol. Then block the endogenous peroxidase. Sometimes tissue is having peroxidase. Tissue is having endogenous peroxidase. In our method, the final stage, I'll come to that later. Final stage, we are use the peroxidase as a label to identify the completion of antigen-antibody reaction. To see the antibody-antigen reaction, as a label, we use the peroxidase. But if the tissue is having endogenous peroxidase, it will mixing up. So this endogenous peroxidase is also giving side reaction or the positive reaction, false positive. So this should be stopped. How you are going to stop that one? The tissue is having peroxidase now. We are adding hydrogen peroxide. When you add the hydrogen peroxide, what will happen? The peroxidase in the tissue will react with the hydrogen peroxide and cancels. Then after that, that reaction will not occur again, right? So that you can block the endogenous peroxidase by addition of hydrogen peroxide and methanol mixture. Then sometimes you get the unnecessary reaction. Finally, when we add the antibodies, what will happen? These antibodies come and bound and giving some non-specific reaction, right? Finally, when we are adding the final antibodies, these antibodies not only with the antigen, there are some other non-specific antigen found in the tissue. So those should be blocked. How you are going to block those unnecessary non-specific binding? Adding normal serum or buoyant serum albumin. When you add buoyant serum or normal serum, what will happen? This will go and bind to the non-specific binding sites and cover these things. After that, that problem doesn't arise. Then after that, perform required antigen retrieval. Antigen retrieval means when you do the formalin fixation, what will happen? The formalin, it covers the epitopes of the antigen. Antigen epitopes are covered. It is called masking. Antigen epitopes are masked. The masking should be removed. Otherwise, antibody cannot come and contact with the antigen. So it is called antigen retrieval. Antigen retrieval means in the Parapet technique, antigen is masked by the formalin. That masking should be, the mask should be removed. That is called mask is removed, unmasked. Unmask is done by the method called antigen retrieval. There are two methods. Proteolytic enzyme induced retrieval. Proteolytic enzyme induced epitope retrieval. Proteolytic enzyme induced epitope retrieval. Other one, heat induced epitope retrieval. Heat induced epitope retrieval. There are two methods. By these retrieval methods, you can unmask the antigen. Then it will help to antibody to come and react with the antigen. Then add the primary antibody. Then wash it in between. You have to wash it thoroughly with the buffer. In between all these things, you have to wash with the buffer thoroughly. Otherwise, you get false positive. Then at the primary antibody, wash with buffer. Then after that, secondary antibody, wash with buffer. Then reaction completes. Then after that, at the chromogen and the substrate, the chromogen substrate is called diaminobenzidine. That is the chromogen. Diaminobenzidine, DAB solution. We call it DAB solution, carcinogenic chemical. That is the chromogen. And the substrate, we are adding peroxidase no label. Then substrate is hydrogen peroxidase. Then when we add the chromogen substrate, it consists of two chemicals. One is chromogen, diaminobenzidine. Other one substrate. Substrate is the hydrogen peroxide, which is a substrate for the hydrogen peroxidase enzyme. Then after that, wash it thoroughly, counter stain with hematoxylene, dehydrate, clear, and mount in DPX and microscopic observation. So these are the steps in the immunohistochemistry. So there are different methods: peroxidase, antiperoxidase method, biotin-avidine complex method, labeled streptavidine biotin method, alkaline phosphatase, anti-alkaline phosphatase method, polymer-based method, and there are etc. The different methods are there. But in Sri Lankan setup, mostly they are using biotin-avidine complex method or the labeled streptavidine biotin method. Second and third methods are used in the most of the Sri Lankan laboratories, right? So this is the method. So this is a tissue. Tissue is having proteins. Antigens are proteins. These are the antigens, right? So this antigen, when we add the primary antibody which is specific to this antigen. Suppose this is S100 or Y-mentin or maybe CD34. So that type of antigen. So this is the particular specific antigen for that one. There's a primary antibody. Actually, this is called indirect labeling. If it is direct labeling, the primary antibody should be labeled. But here, primary antibody is not labeled, right? This is indirect labeling. So this is the antigen, right? So this is the specific antibody to that one. So allow it to react, right? Then after wash thoroughly, if the antigen is not there, once you washing, antigen-antibody complex is not formed. So this will be washed off. So if the antigen is there, antigen-antibody complex is formed, then even with the washing, it doesn't wash away. It will remain. Then after that, we add the second antibody, secondary antibody, which is labeled. Secondary antibody is labeled with the enzyme. What is the enzyme? Peroxidase or alkaline phosphatase. In Sri Lankan setup, mostly peroxidase. So antigen, antibody, primary antibody. Then when we add the secondary antibody react to the primary antibody. This is combined with the peroxidase enzyme. Then after that, we add the substrate and the chromogen. Then once we wash it, if the antigen is there, the whole thing will not be washed away. If it is negative, if it is no antigen, the whole thing will be washed. So in the presence of antigen, this complex will be stable. Then what will happen? The substrate means peroxidase no enzyme. Then what is the substrate for the peroxidase? Hydrogen peroxide. Hydrogen peroxide is substrate. Then hydrogen peroxide and the color product is there. Hydrogen peroxide and the chromogen, the DAB is there. So DAB is the color agent. Color agent and substrate is there. When in the presence of enzyme, this will give the colored end product. So when you examine under the microscope, you can see the color. So this is the technique. This is the whole procedure in the immunohistochemistry. So fixation can be done in the aldehyde fixation or frozen technique. You can fix with the liquid nitrogen. So this is a fixation I just mentioned, but not very much important. So you can say in this one aldehyde it used. So what happened? There may be, but this is good architecture. But when you are doing the frozen sections, very difficult to cut, then very difficult to get the good section. The morphology is not good. Section in paraffin and frozen. Paraffin wax must heat process through xylene. We are using heat and alcohol. Then ruin some alcohol antigens. But most commonly used technique is paraffin technique. But if not stored more than 2 weeks, lose antigenicity after that. So you should not store more than 2 weeks. If you are using more, if you are using after 2 weeks, most of the antigenicity will be lost. That means don't use the tissues after 2 weeks time. Frozen, poor morphology, cutting difficulties, and the poor resolution, and it need the special storage. So that's the reason we very rarely only you are using frozen techniques, but you are using parapin sections. Here you can see sometimes the antigen will be masked, but it can be recovered by the antigen retrieval methods. So this is the resin method, very rarely done. So antigen retrieval. What is antigen retrieval? When you add the formalin, antigen epitopes are masked. You have to unmask the thing before start. It is called antigen retrieval. It can be done in different techniques, 2 different techniques. One is called using proteolytic enzyme method. Other one is called heat-mediated antigen retrieval. Here we are using in the proteolytic enzyme method, different enzymes are used. These enzymes are doing the retrieval. Second one, heat. Heat does the retrieval. So in the proteolytic enzyme method, you can use the trypsin, chymotrypsin, protease, or the pepsin as the enzyme. These will retrieve the antigen epitopes. In the heat method, many heat methods you can use. You take the slide and immerse in the buffer solution, and after that keep the whole thing in the microwave oven or the pressure cooker or the steamer or the autoclave or water bath. You can take the slides and arrange in the tough slide containing, you can contain the slides filled with this buffer, citrate buffer, EDTA or EDTA buffer, and whole thing can be kept inside the microwave oven, pressure cooker, steamer, autoclave, and the water bath. Then after that, it will retrieve the antigen. So heat-mediated antigen, microwave oven heating methodology, pressure cooker methodology, steamer antigen retrieval methodology, water bath methodology, autoclave, and sometimes combination of trypsin digestion and microwave antigen retrieval. That also there. Combination of trypsin and heat, both can be there. That antigen retrieval, higher heat-induced epitope retrieval. This is PIRE, proteolytic enzyme epitope retrieval. So in that one, sometimes it destroys some epitopes by the proteolytic enzyme, bad for morphology, but here it's good. Heat-induced epitope retrieval is good. Then improving antibody penetrance. Sometimes the antibody does not go into the nuclei. Sometimes the antigens are present in the nucleus. So antibody is difficult to go to reach the nuclear antigen. So in that time, we have to improve the antibody penetration. Antibody penetration can be done by using detergents. Most popular Triton X or Twin. Then what will happen? It will allow the membrane to enter the antibody and go into the nuclei and react. So acetone, methanol, precipitate protein outside the cell membrane, more accessible. Or saponin, you can use a saponin. It punches hole in the cell membrane, holes close up when removed. Then punches the hole in the cell membrane. So it can, as a result of that, then antibody can easily contact with the antigen. Then there are 2 things. This is very important, proliferative markers and prognostic markers. Proliferative markers means cell proliferation found in the cancer. The cancer cells are uncontrollably proliferate and uncontrollable divided of cells. So that means high mitotic activity. So that can be observed by doing a marker, using a marker called Ki67. Ki67 is a protein that found only in the cell that are dividing. A high Ki67 proliferation index means cells are dividing quickly. That means cancer is fast growing and cancer is fast growing and very virulent. And that cancer is like to grow and spread fastly. So Ki67 is a proliferation index over 30% is typically considered high. So you are measuring Ki67. For that one, you can predict about the dividing of cells, how rapid dividing of cells, or what is called the dangerous of the cancer. That can be detected by using a proliferative marker, example Ki67. So there's another thing called prognostic marker. Prognostic marker. What are the prognostic markers? It's defined as a marker that is used to monitor and predict the progression of disease. The progression of disease, monitor and predict. You can monitor and predict the progression of disease by using a prognostic marker. That means if you do the prognostic marker, you can say whether the treatment is good or whether the progression of disease good, like that. Prognostic marker is one of that indicates that increased likelihood of future clinical events, disease recurrence or progression in the identified population. That means if you get the biomarker, prognostic marker is very high, that means you can say prognosis is good. Prognosis means treatment to the what is called response to the treatment. If the prognostic marker is low, that means prognosis is bad. Prognosis biomarkers are measured as a defined baseline, which may include the background treatment. You can decide the background treatment by doing after the prognostic marker. For example, estrogen receptor or the progesterone receptor or the HER2 receptors. These are the prognostic biomarkers. If the prognostic biomarkers are present, then you can use hormonal therapy. That means that is good. So presence of prognostic markers will be good for us. Then different types of cancers are there. List of epithelial origin. If the neoplasm is in the epithelium, we call it carcinoma. If the neoplasm starts from the hematopoietic cell, if it is origin from the hematopoietic origin, we call example lymphoma. If the melanocytic origin, we call it melanoma. If it is mesenchymal origin, we call sarcoma. In the central nervous system, example glial origin, example is a glioblastoma multiforme. Like that, from the different places, different cell layers, cancers are formed. You can identify these things in different methods. So if it is a epithelial cell origin, carcinomas are called. What are carcinomas? Carcinomas are the neoplasm with epithelial origin. How you identify the carcinoma? Carcinoma by the especially with the CK, cytokeratin. Cytokeratin is a marker which is currently used. CK, cytokeratin designation system is known as small catalog. There are about 20 cytokeratins are known, divided into type 1 and type 2. Type 1 means acid keratin. There are 12 types. Out of 20, 12 are acidic keratins. 8 are type 2 basic keratin. CK1 to CK8. 8 types are basic keratins. These are type 2. From 9 to 20 are 12 types. These are called acidic keratins type 1. So these are important to diagnose the carcinomas. That means epithelial origin neoplasm. Also divided, this cytokeratin can be divided into according to the high molecular weight CK, high molecular weight cytokeratin or the low molecular weight cytokeratin. First, now we can identify the cancer by the tiered fashion, just like tier. First tier, second tier, like that. First tier designed to place a neoplasm into one of the major diagnostic categories. What are the neoplastic? These are the major categories. These are the, first of all, you have to see which type of, whether it's a carcinoma, whether lymphoma, whether it's a melanoma, whether sarcoma, or whether glioblastoma. That's the first tier. That's the first tier. That's the tiered fashion. Then second tier subclassify the neoplasm within the category determined. So first one, we do the cytokeratin. Then if the cytokeratin, mostly carcinoma. Then after, to subclassify, there are different antigens to be studied. So like that, you can do it like that. So second tier subclassify the neoplasm within the major category. Panel of stain used in the first tier in the evaluation include cytokeratin stain, positive in all carcinomas and rarely neoplasm in the other categories like that. Stain of hemopoietic cells, example CD, mostly CD. CD45 or leukocyte combination LCA. Stain for melanocytic differentiation S100 and HMB45 like that. Stain for mesenchymal differentiation Y maintain. For the glial differentiation GFAP. Can you remember now? So like that, different first tier, second tier like that, you can get the major type you can identify. And after that, second minor category. Right. Some neoplasia may show immune reactivity for more than one of the HCA markers. That's a problem. Sometimes we expect only one type of immunomarker will be there, but sometimes it will get confusing. Why? It may contain more than one type of immunomarkers. Example, glioneoplasm. We expect the GFAP. We expect the GFAP in the glial, but sometimes it contains cytokeratin. So there may be confusion. So some non-melanocytic neoplasm contain HMB45. Rare carcinomas giving glioblastoma. Some breast carcinoma, GFAP. GFAP from the neural cells, but breast also giving GFAP some cases. Many neoplasm shows S100. So these are the, due to these things, there are some confusion. So you must have the clinical, these things, HN is right, and all these things with the qualified person can go for the complete diagnosis. Important for entire panel in the first round to be familiar with the patterns of combined positivity with specific neoplastic categories. Once the basic category of neoplasm determined, it is useful to analyze more direct set of IHC for further characteristic neoplasm. Antibodies various cytokeratin like CK7, CK20 used to help differentiate the various subtypes of carcinoma. I told you carcinomas by the cytokeratin to identify the subtypes CK7 and CK20. Sarcomas can be subdivided into those that show smooth muscle differentiation, endothelial differentiation, etc. Many lymphoid markers are now available for sub-specification of lymphomas. So generic categories, small round cell tumors, large polygonal spindle. Here I am taking small round cell and spindle cell tumors as example. I am not bothering about other thing. I have taken example, small round cell and the spindle cell. We'll see what it is. In children, most common poorly differentiated neoplasm consists of small immature epithelial cells with relatively round nuclei and scanty cytoplasm. So you can see relatively round nuclei and immature. That means very large, immature round nuclei and scanty cytoplasm. So as a result of that, you can see small round blue appearance. Small round blue because nuclear is blue. So you can see the small round blue cell. So we call it small round blue tumors, small cell carcinomas. So example, Ewing's sarcoma, neuroblastoma, and other primitive neuroectodermal tumors, lymphoma, rhabdomyosarcomas are desmoplastic small round cell tumors. Then those type of diagnosis of small round cell tumors can be diagnosed with the different antigens like vimentin, CK, EMA, NSC, myogenin, despin like that. These are the tumors, neuroblastoma, Ewing's sarcoma, like that. These are the diseases. I just giving for the example, not necessary to cram, not necessary to by heart study, just example for your future readings. I don't think these things will be coming to the exam. So then next one, what is called that, this like, this composed of this is composed of thin, elongated, arranged in the bundles, occur at any site of the body, subcutaneous tissue, deep soft tissue, viscera, central and peripheral nervous system. Most are mesenchymal and neuroectodermal. So differential diagnosis include smooth muscle differentiation, tumor of new sheath origin, gastro. The cells are arranged in composed of thin elongated cells arranged in bundle. So we call it spindle cell carcinoma. It arranged like a spindle. We call it spindle cell carcinoma. So this one example, I am giving the antigens, but not necessary to keep by heart. Just example for your knowledge. I don't think this is, there are some antigens. This will be helpful to the people who are working in the immunohistochemistry department. So example, small cell carcinoma, small cell neuroendocrine, malignant melanoma, lymphoma, granulocytic sarcoma, neuroblastoma, primitive neuroectodermal tumors, rhabdomyolysis sarcoma. Right. Then how you are going to differentiate carcinoma from the other things? Carcinoma from the other neoplasm. This will be little important. The carcinomas always CK positive. CK means cytokeratin positive. Cytokeratin positive in carcinoma. So if the cytokeratin is positive, you can differentiate it carcinoma from the sarcoma, melanoma, and lymphoma. So other three can be identified using vimentin, S100, and leukocyte common antigen. When you are doing these four panel of antigen, so you can give the complete diagnosis of the whether it's a carcinoma, whether it's a sarcoma, whether it's melanoma, and the lymphoma. So differentiate the carcinoma from the sarcoma, melanoma, and lymphoma, CK will be sufficient. Then you can use the IHC for the diagnosis infections caused by the infectious diseases, because sometimes some organisms difficult to grow and require long incubation. Example, so in that time, we can use the IHC. Example, bacteria, Helicobacter pylori, this causes the gastritis, or Treponema pallidum, that's the spirochete for the venereal disease, what is called that what is called sexual disease, transmitted disease, syphilis, and the some mycobacteria. Those cannot be grow or the long incubation. So definitely go for the infection IHC. Fungi, Histoplasma capsulatum, coccidioides, virus, herpes simplex, cytomegalo, and hepatitis B and C, parasites, Toxoplasma gondii, neurocystic carini. So if a question is asked, what are the uses of IHC? Where are the uses of IHC in identifying infectious diseases? You can mention, you can say normally difficult to grow and require long incubation. As a result of that, traditional method will not be help. So definitely you have to go for the IHC. There are 4 types I have given: bacteria, fungi, virus, parasite. So you can give at least 2 examples for each. Bacteria 2 example, fungi 2, virus 2, parasite 2. Then some brain diseases, like if you can name this disease will be enough. Neurodegenerative disorder, Alzheimer's disease, Lewy body disorder, frontotemporal degeneration, and Huntington's disease. These are the brain diseases. These are the non-neoplastic brain diseases. Those also can be. So if there's a question, what are the non-neoplastic brain diseases can be identifiable by the IHC. So if you can name these things will be enough. Then muscular dystrophies, progressive loss of skeletal muscle function. The muscle function will be progressive loss. Example, dystrophinopathies and the sarcoglycanopathies and myrcene deficiency. So in this one, Duncan muscular dystrophy and Baker muscular dystrophy. So this is dystrophinopathy. Second one, sarcoglycanopathy, deficiency of any of the sarcoglycans protein. Third one, myrcene deficiency, autosomal recessive due to the mutation in the alpha-2 laminin gene of the chromosome 6. So if you can name these 4 diseases will be enough. So these are the muscular diseases. So these are the regarding B lymphomas, mostly CD markers. Mostly CD markers. You can see different type of lymphomas here, B cell, peripheral B cell neoplasm for follicular lymphoma, small cell lymphoma, like that number of lymphomas are there. So they can be identified by doing the panel of antibody. You must write that lymphomas can be identified by using a panel of lymphomas, not only the positivity, even the negativity also. Now in the precursor cell lymphoma is identified by CD20 negativity. That means not only the positivity, negativity also important to diagnose in the B cell lymphoma, right? So if you can mention about 3-4 markers and 3-4 diseases will be sufficient. So panel of antibodies here again, panel of antibodies are included for each case. Ultimately, the final diagnosis made with the aid of all positive and negative results. For example, when diagnosed DCBL, all B cell markers positive and negative for CD5, cyclin D1 and CD90. Like that. So you can identify like that. That means not only positivity, negativity also. So Hodgkin lymphoma. So there are different Hodgkin lymphomas there. This can be used by using these CD markers. Most of these CD markers, you must be able to identify, name 3-4 markers of these things. Then this is the practical application of immunohistochemistry. Special diagnosis of undifferentiated tumors. Sometimes tumors are undifferentiated, cells are not differentiated. So very difficult to diagnose. So in that case, to give the diagnosis, we can do the IHC. Then detection of micrometastasis. Metastasis means when the cancer starts from one place, example, prostate or colon. Then second time, it originates from the second faraway place, maybe brain, liver or lung. It is called metastasis, secondaries. Sometimes you get the micrometastasis, that's very early stages. So detect the micrometastasis, IHC is done. Then there are two types of cancer. One is called in situ carcinoma, other one is called invasive carcinoma. To differentiate in situ carcinoma from the invasive carcinoma, we can do the IHC. Then viral antigen. To look for the viral antigens, so there are no other method. You have to go for the antigen IHC. Then receptor stage breast carcinoma. I told you as a prognosis marker, receptor status in breast carcinoma, ER and PR and HER2. Estrogen receptor, progesterone receptor, and HER2. For that one, receptor status, it can be identified by, in the breast carcinoma, can be identified by the IHC. And detection of oncogenic protein, mutant antigen oncogenes, and the proportion of cells in a tumor. So these things can be, so these are the practical application. This type of question you can expect, what are the practical application of IHC. Then this is very important. So in the immunohistochemistry, every protocol step is important. Fixation, processing, section cutting, incubation, then adding primary antibody, secondary antibody. That means each and every protocol is step important. So weak or no staining, non-specific staining, high background, over staining need to be troubleshoot. You have to troubleshoot where weak staining or no staining, non-specific staining, or high background, over stain. In those conditions, you have to do the troubleshooting. Common errors in IHC as non-specific stain, tissue artifacts, inadequate inactivation of endogen peroxidase activity and cross-reactivity. What is non-specific staining? Sometimes the antibody come and bind to the non-specific areas and giving background, high background, or tissue artifact, some tissue artifacts. Inadequate inactivation of peroxidase. Sometimes tissue is having peroxidase. That peroxidase bind to the chromogen and give the wrong or side reaction, and the cross reactivity. The secondary antibody will come and bound to the tissue, not to the primary antibody. some other area in the tissue and give the cross-reactivity. Like, so these are the common errors in IHC. Inadequate deperipination may cause spotty, uneven background staining in the IHC experiment. If the deperipination is wrong and inadequate, there may be errors. Duration of fixation, that is important. Fixation formula important. Tissue to fixation ratio. Those things are affect the extent and intensity of the IHC. Duration of fixation, fixation type, tissue to fixation ratio. Those are affect the extent and intensity of the IHC. And always, this is very, very crucial. Each and every set, every batch, positive and negative control should be mandatory. And each and every batch. And the IQC and EQ is vital. So this is very, very important. This is the most important thing in the IHC. Why? This is a very expensive procedure. So positive and negative control should be there. If the positive control gives negative or the negative control gives positive, so you reject whole batch. And the IQC and EQ is vital. The reception should be minimized at the high cost. Repetition should be minimized at the high cost time and the manpower. Everything will be wasted if you repeat this thing. So you should be done in the careful manner and should be done in the accurate manner. So one very well-trained person should do these things. And very, very, very important, attention for chemical usage. The most chemicals are carcinogenic. Diaminobenzene, benzidine, that's a color agent, and the xylene and the formalin, these are carcinogenic. And when you have storage and preparation and disposable, you have to, those things are very, very important. Handling and disposal carcinogenic chemical, DAB, xylene, formalin should be done very carefully, right? So when you are measuring, weighing DAB, the balance, when you are using this thing, balance, electronic balance, prevent inhaling, and xylene also, and the formalin disposing. I discussed in the previous presentation that should be applied here also, how the xylene and formalin disposal. So if somebody asks, how you dispose the carcinogen, how do you dispose the chemicals in the IHC? So that is the answer. That you have to tell about the DAB carefully. DAB should be carefully what is called put into the dispose without inhaling, without handling. When you are handling, you have to take care. And the xylene and formalin I have mentioned in the earlier one. This is the end of the discussion. Any question you can query now.